In this video, we're going to look at ionic bonding. In ionic bonding, what we're talking about here, we're looking at what happens when a metal bonds to a nonmetal, which is different than covalent bonding. Covalent bonding are nonmetals bonding to other nonmetals. So we got a metal bonding to a nonmetal. Here's the thing we've got to realize. Metals are elements that lose electrons, therefore they become positive. Nonmetals are elements that gain electrons, therefore they become negative. So what happens, they combine so that we get positive negative charges, and these positive and negative charges cancel out, or if we think as a magnet, opposites attract. And when the opposites attract, that's our bond, that's our glue that holds those atoms together. Here's the thing to remember. What's the most likely way that an element is going to form an ion? Well, it's the easiest way that an element gets to P6. So you may need to go back to a little bit of Chapter 4 and Chapter 5 in terms of what are they going to gain or lose. You know, we got group 1 metals or S1, they're going to lose 1. Group 2 metals and in S2, they're going to lose 2. So you need to maybe refresh a little bit on what that is, and obviously we can talk about it in class. The other thing we want to think about is a term called formula unit. This is the name that we give to the actual formula or the ratio of ions in an ionic compound. It's not quite the same as a covalent compound, because in a covalent compound you have discrete little objects. Imagine you have a handful of water. It'd be like having a handful of M&Ms. There's a whole bunch. It kind of looks like one big glob, but there are individual pieces. In the case of an ionic compound, you have things like salt crystals. Well, what you have is just ongoing wave of sodiums connected to chlorines, connected to sodiums, connected to chlorines, connected to sodiums. So it's like you got a whole bunch of magnets stuck together. That's the difference between a covalent compound versus an ionic compound. To figure out how do they bond together, how do metals bond with nonmetals? Well, here's two things we're going to look at. We're going to use electron dots again, just like we did in covalent bonding, and we're going to use orbital notation. Now remember, the orbital notation, just do the noble gas configuration. All we care about are the valence electrons. They're the ones that are going to bond, not the inner shell. So don't worry about, if I have you do iodine, there's 53 electrons. Don't do 53 electrons. Do the noble gas notation. So what do we have to remember? Just like covalent, every element wants to have 8 in its outermost level. It wants to end up with S2P6. The difference again between this and covalent, they're going to gain or lose to get 8, not share to get 8. So what ultimately is our goal? Our goal is to figure out what is the correct ratio of every element so that the charges cancel out. Everything equals 0. The positives are canceled out by the negatives. The negatives are canceled out by the positives. Because again, we're not sharing to get 8. Something's got to lose, something's got to gain, and they need to offset each other. Okay, so we have a net change of 0, or a net value of 0. So let's look at a couple simple examples. Salt, plain old NaCl. So I've got here on the left-hand side the electron dot structure for NaCl and the noble gas orbital notation for chlorine and the noble gas notation for sodium. So what are we trying to solve for? We are trying to solve for what is the ratio of atoms, or ultimately, what's the formula? Na what? Cl what? Is it Na1, Cl2, Na2, Cl? Right? You know what it is, okay? But we're going to kind of go through the process. So here's the difference when we do electron dots. We see here that sodium has 1 electron in its outer valence level. If it loses this 1, what does it have left? It has 0 in its outer shell. Well, if it has 0 in its outer shell, what's now in the previous shell? Well, the previous shell would be an S2P6. That's what it wants. Chlorine is an S2P5. It needs 1 more to become S2P6. So what happens? Sodium gives up that electron to chlorine. This is not a two-way street. It is not a double-sided or double-ended arrow. The electron leaves sodium, goes to chlorine. So what have we just created? We've just created a sodium atom that's positively charged, and we've just created a chlorine ion, which is negatively charged. We have a positive and negative, opposites attract. The second thing we notice is they formed in a 1-to-1 ratio. There's nothing else left over. If we do orbital notation, we see here, well, if sodium loses this one 3s electron, what's it left with? Neon's configuration, which is 2s2, 2p6, which is what it wants. If we give this electron to chlorine, or chlorine takes it, its outer electron configuration is now 3p6. That's what it wants. So both scenarios tells us exactly what we want, which is when sodium and chlorine combine, the only way they combine is in a 1-to-1 ratio. So their final formula, Na1Cl1, or simply NaCl. Just like anything else, we don't write ones. You don't have to write ones. It's assumed that it's a 1 if there's no subscript. Yeah. So there's an example of how we do sodium and chlorine. It's a little bit easier. You can actually, and you'll see here in a little bit, we can do some math instead of doing all this extra drawing. All right, so let's look at calcium and chlorine. What we need to figure out is what is the ratio. It is not necessarily a 1-to-1 ratio. We need to figure out what is that ratio proportion. So if we see here, we need calcium. It has 2 electrons it needs to lose. Well, okay, one will be lost to that chlorine. Good. That chlorine's checked off. It's got P6. The problem is the calcium's not P6. It's now just an S1. So it's like losing this 1 electron, and it goes there, but the problem is there's still an extra electron left. So where does this second electron go? Because it can't stay in S1. It's got to go to P6. Well, what happens? That electron has to go to another chlorine. So what we're just proving here is the only way chlorine and calcium will bond together is if it is in a 1-to-2 ratio of calcium to chlorine. Why is that? Because calciums have 2 electrons to lose to go to P6. Chlorines can only accept 1, and everything has to cancel out. There has to be a net 0. So the only way that's going to work is 2 chlorines will bond with a calcium. So we ended up with CaCl2. Now, I've just done 2 examples. Back up. I just did an example for sodium and chlorine. Well, now, what holds true is every element in sodium's group and every element in chlorine's group are going to do exactly the same thing. Potassium and chlorine, lithium and chlorine, potassium and fluorine, rubidium and iodine. You put elements in those 2 groups together, they do exactly the same thing because their configuration ends the same way. You come over here, calcium and chlorine. You pick any element in calcium's group. It's an S2. It'll behave exactly the same way that the calcium will, whether it's magnesium or anything like that. All right. What I'm going to have you do here is I'll have you write this down. I want you to figure out, number 1, doing electron dot, and number 2, doing orbital notation, okay, and do the noble gas, do the shorthand. Figure out what the actual ratio will be for aluminum and oxygen, and then ultimately what will the formula be. Okay? So I'll have you pause this, work on these, and I'll quickly put up the answers, and we can go from there. Okay, so we'll work these out here. Remember, we're not going to do a ton of these because we're going to look mathematically how to do this instead of draw these. But if we look here, I've got 2 aluminums and 3 oxygens that are needed to bond things out. Each aluminum has 3 to lose. The oxygens can only gain 2. So we got a 3 and 2. We think of 3, 2, oh, 6 has got to match somehow. You're right. So what we figure out here, the ratio is 2 to 3. So Al2O3. Now, we draw the orbital notation. This is where it gets kind of messy. Again, I'm not going to have you do a ton of these, but we do need to be able to not only determine how many electrons are being moved, but also where they're at from the orbital perspective. So if we see here, we have this first aluminum up top. It has 3 electrons, and we see where they go. There's number 1, 2, 3. That aluminum's set. Okay? This oxygen is set. Then we look at the next aluminum. It has 3. 1 goes there, 1 goes there, 1 goes there. So now the first aluminum set, the first oxygen set, the second aluminum has lost 3, the second oxygen has gained 3, and now the third oxygen has gained 3. So again, we're in that 2 to 3 ratio. Okay? Very much like a puzzle piece here as we put things together. All right, now, how can we do this faster, less writing, all that stuff? Well, we want to think in terms of math. Here's the math. The metal's going to be positive. The other thing's got to be negative. Plus minus has to equal 0. Okay? So if we're looking at this, what we want to show is, all right, sodium has 1 dot. That means it wants to lose 1. Okay, it's close to being empty. Chlorine has 7. It wants to gain 1. Calcium has 2 dots. We know it wants to lose. It's going to be a plus 2. Aluminum has 3 to lose. All right, it wants to be a plus 3. Oxygen, it has 6. It wants to gain 2 to get to a P6. So what we want to start thinking about is, instead of drawing dots, think of the numbers. Plus 1, minus 1. Plus 2, minus 2. Okay? And we're going to try and add the positive and negatives together until we get the right combination that equals 0. So what it's going to be is, we might have some, again, if using too much algebra here, some coefficient of A times the positive metals plus some coefficient of B times the negative ions, all equals 0. Okay? We've got to figure out what the values of A and B are. All right, so here's what we're going to look at. If we start to do these, we're going to basically take and cross charges and do the math to give us the same results as our coefficients or our electron dots do. If we go back to the 3 example you've already seen, using electron dots, we figured out it was NaCl, CaCl2, and Al2O3. We also did the orbital notation, which stunk because you had a lot of drawing to do. Well, now here's the terms of math. We have a plus 1 and a minus 1. If we have 1 of each, what do we get? A positive 1 plus a negative 1 equals 0. We have a plus 2. How do we cancel out a plus 2? We need 2 minus 1s. We have a plus 3 and a minus 2. How do we get a plus 3 and a minus 2 to cancel out? Well, 2 plus 3s times 3 minus 2s. Right? Just simple algebra in our head. That's what we're doing right here. Okay? So, for the most part, you should be able to see that that's what we're going to do. If we have sodium, it's a 1, and chlorine's a minus 1, 1 of each equals 0. What's even a quicker way to do this? Well, if we cross the charges, they become our subscripts. Okay? So, after you've kind of looked at this, let's just back up a step. Let's say, all right, what's an even simpler way to say it? The charge on sodium becomes the subscript on the other one. The charge on chlorine becomes the subscript on sodium. Now, not the sign, just the value. A 2 on calcium becomes a subscript on chlorine. A 1 on chlorine becomes a subscript on calcium. A 2 on the oxygen becomes a subscript on aluminum. The 3 on aluminum becomes a subscript on oxygen. That always holds true. One other thing, you don't have to say 1, you could just say NaCl, and you could just say CaCl2. Here's the only thing you want to kind of watch out for. Let's say we put calcium with oxygen. We don't really want to use coefficients of 2 because it didn't take two calciums to cancel out two oxygens. It took one of each. So really the correct formula for calcium oxide, okay, calcium and oxygen, is CaO, one of each, because a plus 2 is canceled out by 1, 2 minus. So as we're doing this, this is how we want to kind of approach those examples. And we could do a ton more in the book. This leads right in the very first section of chapter 7. Now, last thing we'll say here. There's only one common ion for groups 1, 2, and then 13 through 18. The S block and the D block. Sorry, S block and P block. Now, the D block, what the heck goes on there? Well, some multiple things happen. The most common is plus 2. So as of right now, if you run across it, it's a plus 2. Iron, copper, chromium, zinc. There are other possibilities based upon their S2, D10, D1, D2 configuration. We will talk more about that in chapter 7. Okay? So, little overview there about ionic bonds, how the elements bond together, and how we can kind of figure out what their formula is. The next part will be, we'll look at some polyatomic ions, and then a little bit about some of their properties.